I'm going to work some of our Chapter 13, Properties Solutions. I commonly call this the colligative properties chapter. We're going to practice test A and just taking a look at what our last test of the first semester will look like. So colligative properties, practice test A. One of the first testing objectives has a good reminder about the intermolecular attractions involved in thinking about whether a solution will form. We always think about the saying, likes dissolve likes. So the little helpful hint here, likes dissolve likes, is simply suggesting that when I consider if a solution forms, polar will dissolve in polar, nonpolar will dissolve in nonpolar, but not one of each. Number one overall says, indicate the solute-solvent interaction that should be most important in each of the following solutions. Might be a good time to just review what the solute-solvent interactions might include. We know that one of the first is called the London dispersion force, or simply dispersion forces. Those are based on every substance has a dispersion force, and it's the only one that a nonpolar would have. So dispersion forces are those attractions between molecules due to a temporarily induced pole just by coming near each other. They're instantaneous and then they fall back to their natural state. So dispersion forces are the only type of intermolecular attraction for nonpolar molecules, but all molecules do exhibit them. From there, we talked about dipole-dipole interactions, which is another way of saying polar with polar. A dipole is a molecule that has an area that's positive and an area that's negative. Polar molecules exhibit dipole characteristics. Hydrogen bonding. Hydrogen bonding is when we have either a hydrogen attached to a fluorine, hydrogen attached to an oxygen, or hydrogen attached to a nitrogen. Those three most electronegative elements. Now the attraction is actually between molecules, but the criteria for hydrogen bonding would include HF, HO, or HN. These are collectively known as van der Waals forces, exhibiting intermolecular attractions between molecules. There is a fourth category. It's called ion dipole attraction, which specifically has to do with ionic salts. So if I think about a metal to a nonmetal, any type of compound I'm writing with a positive hook to a negative, crisscrossing charges, those are indeed ionic compounds, probably called salts in everyday language. And of course, something like sodium chloride, ionic, dissolving in water, which is polar, we'd have an ion dipole. So when a salt goes into a polar solvent, the intermolecular attraction is an ion dipole. It is left in its own category. So intermolecular are the van der Waals, and a salt going into a solvent would be known as ion dipole. So let's take a peek at letter A, hexane and heptane. Hexane, the prefix for 6, and heptane, the prefix for 7. We can clearly see that if I were to draw these hydrocarbon chains, 1, 2, 3, 4, 5, 6. We just have a straight chain. 6 carbons in a row is hexane. And heptane would have 7 carbons in a row, but still a long chain of a carbon backbone. We have a nonpolar molecule with a nonpolar molecule. What is the intermolecular attraction that would allow them to form a solution? But a London dispersion force. Dispersion forces are the only intermolecular attraction between nonpolar molecules. So the answer here is a dispersion, or London dispersion. HCl and water. Well, you know, I know that water exhibits hydrogen bonding, but HCl does not exhibit hydrogen bonding. So the one that they have in common, the solute-solvent interaction, would simply be a dipole-dipole. So a dipole is a polar molecule. Now I know water within itself, water could attract itself with hydrogen bonding, but there is no hydrogen bonding criteria in both of those, so the strongest intermolecular attraction they share is a dipole-dipole. Ethanol in water. Well, ethanol does meet the criteria, see that OH at the end? It does meet the criteria of a hydrogen bond. It is a polar molecule, so not only does it have dispersion, it has dipole, but it does meet the criteria for a hydrogen bond, an O to an H. Of course, water, I mentioned just a moment ago, also meets that criteria for a hydrogen bond. So the strongest intermolecular attraction they have in common is hydrogen bonding. Calcium chloride in water. Now again, notice this is an ionic compound. We wrote calcium, which is a metal, chloride, which is a nonmetal. We wrote that formula based on charges. This is an ionic compound being placed into a polar molecule called water. This intermolecular attraction is called an ion dipole. So we ended up showing one of each in our particular model. Let's take a peek at the second question. By referring to the figure below, determine whether your addition of 40 grams of each of the following solids to 100 grams of water at 40 degrees Celsius will be saturated or unsaturated. Saturated, holding the maximum amount possible at a specific temperature. Unsaturated, there's room for more solute before the solution becomes saturated. So room for more. Now notice here we have the unit for solubility, and I know this appeared on our last test. Solubility is generally given in grams of solute per 100 mils or 100 grams of water. Those are the units given for the term solubility. So it's asking us, if I indeed put 40 grams of the solute, see where I'm pulling that, 40 grams of each of the following solutes into 100 grams of water, and that's what it's telling us on the y-axis, that we have 100 grams of water, is the solution ending up to be saturated or unsaturated? Well, in the first salt, sodium nitrate. Let's take a moment and actually find sodium nitrate of all the salts that are listed. NaNO3 I see kind of right here on this line. Alrighty, so there's the curve that I'm looking for the letter A, sodium nitrate. At 40 degrees Celsius, let's skim up and get to the 40 grams, kind of just come across 40 degrees and 40 grams. This is the point that which we're looking at, isn't it? And that point is going to be common for all three salts. So what we're looking at is, in order to be saturated, sodium nitrate can hold up to, golly, over 100 grams of the salt. If I read over here, over 100 grams can fit into the amount of water before it becomes saturated. This point lies underneath the curve, only at 40 grams. There's definitely room for more salt to be added. I can add an incredibly amount of more. I mean, all the way up to the line means there's room for more solute. That means this solution is unsaturated. Let's find the KCl line, potassium chloride, KCl. Help me find it. Oh, right here. There's the KCl line. It actually looks like that dot is falling directly on the line. I mean, it's got to be a close guess. So 40 and 40 actually puts me on the line. That is the direct point of saturation. That solution would be saturated. It's holding all it possibly can. KClO3. Help me find that one. I'm just looking for another highlighter. KClO3, here it is. We are below the line. So this is interesting because I have 40 grams. So this is telling me it's 40 grams are in the water, which is above the point of saturation. Even though it's not a choice, I like the word super saturated, and here's why. If indeed this question is telling me that I did place 40 grams of the potassium chlorate into 100 grams of water and it all dissolved, it's holding more than it should be. It's above the line at the 40-40 mark. This point here lies above the solubility curve. It's holding more than it should. It's called super saturated. Now, we know that those solutions are very unstable, and all it would take is a little bump and all that excess solute would come pouring out. But if indeed it was a dissolved solution, looks clear to the eye, it indeed is super saturated. Letter A, unsaturated. It was below the solubility curve. Letter B, saturated. It fell directly on the solubility curve. And letter C, I'm placing as super saturated because the point is above the solubility curve. Let's keep going. One more set in our first objective. Which of the following pair is most likely soluble in water? Now in this particular version of my practice test, it's saying water, so just to note to self, water is a polar molecule. Likes dissolve likes. I either want to find a polar molecule or an ionic salt. Something built of charges. Letter A says carbon tetrachloride, CCl4. Can you visually see that? Carbon in the center, 4 chlorines around. We could fill out the dots around each chlorine, and we could see a perfectly symmetrical molecule, nonpolar. Calcium chloride is a compound built of ions. Calcium with its +2, chloride with its -1. Calcium chloride is commonly called a salt. Salts dissolve in water. That is an ion dipole intermolecular attraction. Calcium chloride is indeed water soluble. Letter B, acetic acid comes from the polyatomic ion acetate, or barium phosphate, Ba3, PO4 taken twice. Now I know acids are always soluble, but what about barium phosphate? Right off the bat I start thinking about CHOPS and Na, or perhaps you have one of your solubility tables nearby. When I check out my solubility table, barium phosphate is indeed insoluble. Barium phosphate is insoluble. Acids are always soluble. Barium phosphate happens to be the P in CHOPS, the phosphates, so the acetic acid is water soluble. Now it's a weak electrolyte, but it is indeed water soluble. Benzene, C6H6, or glucose, C6H12O6. Benzene is a aromatic compound. Aromatic means that it exhibits resonance. It's that ring, carbon in a 6-ring fashion with some hydrogen sticking out. I'm alternating the double bonds, just throwing some language so hopefully it sticks. It's called resonance. It is a non-polar molecule. Glucose is blood sugar, and indeed that is a polar molecule. Sugars dissolve in water. Ethylene chloride, or ethyl chloride, C3H2Cl, or methane. Thinking of the structure, see how I have a polar molecule with a chlorine hanging off at the end, versus methane, which is a carbon in the center and 4 H's around it. Clearly we see the polar molecule being more water soluble. Sometimes in the practice test or the real test, I might ask you which one is more soluble in benzene, a nonpolar. This example, just be a careful reader, which one is going to be more soluble in water? That's a polar molecule. If you're looking for water solubility, find either a polar molecule or a water soluble salt.